Hi everyone. So this video and slide deck are supposed to serve as an introduction for you to a very important chemistry topic called the mole. So you're going to follow along in your 1.5 handout. Hopefully you all have a copy of that right now. As I go through this slide deck, you're going to listen and follow along for some things to fill out in your handout. There's going to be a couple of practice problems for you to do. If you would like access to these slides in Spanish, please make sure that you can find them on Canvas. So if you have not yet, have whoever's in the classroom with you pause the video. Make sure anyone who needs the slide deck in Spanish can access it from Canvas, and then we'll get going. Okay, so let's talk about what the heck a mole is. To do that, what I would like you to start by thinking about is, you know those games where, like, if you have a big jar of stuff, like you have a big jar of jelly beans, and you have to try and guess how many jelly beans are inside of it? So imagine that you're a person who's in charge of making one of these games. So let's say you have this huge jar. You want to put a bunch of jelly beans inside. People are going to guess how many jelly beans are in there, and then whoever's closest always gets to win a prize. So you, as the person who are in charge of counting the jelly beans, could go about it in a couple of different ways. You could, one by one, take a single jelly bean, put it into the jar, and keep count as you go. 1, 2, 3, 4, and that would take forever, but you could do it. Another way that you could do it would be, let's say, grouping them in tens. You count out 10 jelly beans, and then you put 10 jelly beans in the jar at a time. 10, 20, 30, 40, 50. That's another way you could do it. Another way you could do it is you could go to Costco. And you walk into Costco and you see that huge jug of Jelly Belly jelly beans that they have, and usually it'll tell you how many are inside, and you can just trust it and say, oh, the package says it has 840 jelly beans, so I'm going to say this has 840 jelly beans in it. But that's another way that you could do it. So these things that we're talking about are called counting units. They're methods of counting something. So what is a mole? Well, a mole is just a number that represents a certain amount of things. So just like if you were doing this activity and you put 840 jelly beans, you have 840 things. So a mole is a number of things for a chemist. What number specifically? That monster right there. So this is 602 with 23 zeros after it. So a mole represents 602 with 23 zeros after it things. The way that you say this number is 602 hexillion. That's an insane number to write, right? And we hate writing numbers that are that large. So what we can do is we can also write it like this. It's 602 hexillion things. A nicer way to write it is like this. This is called scientific notation. So you take the first part of your number that has non-zero digits in it, numbers other than 0, and you can write it as 6.02 times 10 to the 23rd. What does that times 10 to the 23rd mean? It just means you take your number, 6.02, and you add 23 zeros after it. You can move your decimal point 23 times, and that gets you your actual value. So this is the number that we'll use to write 1 mole. So 6.02 times 10 to the 23rd things. This is our number in scientific notation. Go ahead and make sure you're filling this in for number 1 on your handout. So that number is a huge number. It represents 6.02 times 10 to the 23rd particles in 1 mole. So we're talking about this as a number of things. What things are we talking about? Particles. So we've been talking a lot about matter, the stuff that makes us up, the stuff that makes up our world. So if you're talking about a mole of things, a mole of particles, it represents 6.02 times 10 to the 23rd particles in a mole. This number can also be referred to as Avogadro's number. So that's a picture of that good-looking dude Avogadro right there on the left. And this is also why Avo has her name. So this is Avo the bearded dragon, specifically named after the scientist credited with determining this number, the number of particles in a mole. So let's think about just how big this number actually is, because it's kind of an insane number to think about, right? So let's say you had, cut off a little bit, oops. So let's say you had 6.02 times 10 to the 23rd donuts. I want you to pause and think about how much space you think this would take up. So do you think it would take up the size of this classroom? We could fill this classroom with 1 mole of donuts. Do you think it would take up the size of your car? Do you think it would take up the size of a football field? So pause the video right here and take 1 minute to think about how much space you think 1 mole of donuts would occupy. Okay, so let's actually figure it out. If you had 1 mole of donuts, 6.02 times 10 to the 23rd donuts, this would cover the entire Earth's surface to a depth of 8 kilometers or 5 miles. That's an insane amount of donuts. So it's much, 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 much bigger than the size of a football field. This campus everywhere would fill the whole surface of the entire Earth. It's a huge, ridiculous number. Let me give you one more example. So let's say you had 1 mole of basketballs. If you had 1 mole of basketballs, you could create an entire new planet made of basketballs that was the size of Earth. One more for you. Let's say you received a mole of pennies on the day you were born, and you spent $1 million every second until the day you died at 100 years old. You would still have more than 99.99% of your money unspent in the bank. So, this is a ridiculously large number. Why do we care? Well, a mole is a chemist's counting unit. Number 4 in your packet. So a mole is a chemist's counting unit. Counting units are created by people to make describing the number of things easier. So there's a lot of common counting units. The most common one that you're probably familiar with is a dozen. A dozen represents 12 things. So take a second to answer these few questions right here. Numbers 6, 7, and 8 in your packet. How many eggs are in 1 dozen? How many cars are in 1 dozen? And which weighs more, 1 dozen cars or 1 dozen eggs? Pause the video here and check in with your table group to answer these 3 questions, please. All right, so hopefully you figured out if 1 dozen is 12 things, there are 12 eggs in 1 dozen. There are 12 cars in 1 dozen cars. And if you're comparing them, obviously a dozen cars weighs so much more than a dozen eggs. A dozen eggs you can hold in your hand. You can't even hold 1 car in your hand. So a dozen cars weighs a lot more than 1 egg, than a dozen eggs. So why would I bring this up? Why would I actually care about this? So remember that a counting unit for a chemist is a mole. 6.02 times 10 to the 23rd. That's a ridiculously large number. 1 mole is so much larger than 1 dozen. But why does it matter? Because we are trying to count things in terms of atoms. We are working with atoms, we are working with particles, which are super, 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 super tiny. So if I'm trying to group things in terms of atoms, which are so tiny, I'm using such a large number because on the actual scale of things, us being able to see it in real life, it really doesn't actually take up that much space. So take a look at these 8 examples right here. I actually have some examples set up for you in the classroom as well so you can see them. These represent 1 mole of different substances: zinc, carbon, magnesium, copper, sulfur, silicon, lead, and tin. I have 3 of them set up for you in the classroom so you can see it, but these all represent 1 mole of their respective substances. Each of these things I can hold in the palm of my hand, and it doesn't even really fill it. So when we're talking about a mole of stuff, 6.02 times 10 to the 23rd particles of stuff, in the macroscopic world, it's incredibly tiny, hardly takes up any space. So this is why it's so important for us to use such a large number, because in chemistry, we're working with super, super tiny things. So let's think about 1 mole of different substances. 1 mole of different substances will have different masses. If I'm comparing something like water to something like carbon, those two things, even though they have 1 mole of particles, do not weigh the same amount. 1 mole of different substances will also have different volumes. They take up different space in the world. You can see this in the examples that I left for you in the classroom. Lastly, 1 mole of substances will have the same number of particles. Even though they have different masses and take up different amounts of space, a mole of any substance will always have 6.02 times 10 to the 23rd particles. Okay, so now let's take a look at a little example. We're going to start out with carbon. So what does a carbon atom actually look like? You did this yesterday in your Build an Atom lab. So this is a carbon atom that has 6 protons, 6 neutrons, and 6 electrons. Recall which of these particles is responsible for the name of the atom, the identity of it. Hopefully you were thinking protons. Protons represent the name or the identity of your substance. So here, any element that has 6 protons is going to be a carbon. The two are linked. Now think about what makes up the mass of any atom. Hopefully you thought protons and neutrons. This is a little review from yesterday. So protons and neutrons are the 2 particles that are responsible for the mass of any atom. So here, the mass number of this carbon atom would be 12. So let's take a look at what the actual symbol for carbon looks like on the periodic table. Looks like this. So there's one number we're familiar with right there. We got the 6. The 6 represents our number of protons, which we also called our atomic number. But what the heck is that number? The mass number of a carbon atom is 12. Why is this 12.011? Those two numbers are not the same thing. So what could this possibly represent? So let's say you have that carbon atom that I showed you before, 6 protons, 6 neutrons, and 6 electrons. That atom will have a mass number of 12. We call it 12 atomic mass units. But there exists other forms of carbon, other versions of carbon. You could totally possibly have another carbon atom that has 6 protons. Protons can't change because then you change the identity. It could have 7 neutrons though, and 6 electrons, assuming this is a neutral atom. So the difference here is in the number of neutrons, which then would make the mass numbers different. Carbon on the left has a mass number of 12, carbon on the right has a mass number of 13. But both of these carbons exist in nature. They just exist in different amounts. So on the periodic table, the number that we see shows up as an average of those values. So I'm going to give you a definition real quick. Definition I'm going to give you is isotope. So an isotope are versions of elements that have the same number of protons, so they have the same identity, but different number of neutrons, meaning different masses. So the number that shows up on the element symbols for any element on the periodic table is an average atomic mass of all versions of all isotopes of all of the atoms that exist in the natural world. So carbon shows up as 12.011 because some carbons have a mass of 12, some carbons have a mass of 13, and there are even more other versions, other isotopes of carbon that exist. So why is this important? Why am I telling you this? Because it's important for what we're about to talk about right now. So, got to get out of here really quick. So the mass number that you see on the periodic table, sorry, give it a second to load. Okay, the mass number you see on the periodic table is also representative of mass per mole for each element. We call this the molar mass. Molar mass, mass per mole. So what this tells us is 1 mole of carbon atoms, 6.02 times 10 to the 23rd carbon atoms, will have a mass of 12.011 grams. The units here are grams per mole, mass per mole, grams per mole. We measure mass in grams. So this is why this is important for me to bring this up, because if we're talking about molar mass, we're talking about moles, and 1 mole of any substance has the same number of particles. So go ahead and pause the video right here, and I want you to do practice problem number 14 on your papers in talking about calcium. Then you can come on back. Okay, so let's do a quick check-in for 14. Hopefully for the name of this element, you said it was calcium. For the atomic number of this element, you can see it represented at the top of the symbol, so this should be 20. And then the molar mass of this element is 40.078 grams per mole. If you didn't put units on your answer for 14C, please go ahead and do that now. You really want to make sure that you're including units in all of your work for chemistry. It's incredibly important. So our molar mass is 40.078 grams per mole. So it turns out that molar mass doesn't just apply to the elements. You can determine the molar mass of entire compounds. So we're going to find out how right now. We're going to do a practice problem, and then you are going to do so many practice problems on your own. Okay, so let's take water as an example. Go ahead and follow along for number 15 in your handout as I do this. You're going to write down, you're going to fill in the blanks of some steps that I left for you on number 15, but I also want you to write down the work so you know how to do these. So step 1, you're going to determine the molar mass of the individual elements in the compound from the periodic table. So if you take a look at a periodic table, you have a bunch of them in the buckets that are on your tables. You can grab one of those, or you can look up to the left-hand side of the room with that huge periodic table on the wall. So if you look on the periodic table, what you'll notice is the molar mass for hydrogen is represented as approximately 1.008 grams per mole, and oxygen is 15.999 grams per mole. So if you look at the periodic table that's in your table buckets, and you look at the periodic table that's up on the wall, not all of the numbers for the molar masses are the same. Some of them are rounded a little bit differently. This just takes into account different precisions, which isn't a big deal. For your proficiency checks, for your tests, whatever in this class, you can use the numbers that are either on the wall, or you can use the ones on in your table buckets. I don't care, as long as you're staying consistent. So the numbers that I'm choosing here are the ones that you'll find most commonly on most periodic tables, so that's why I'm going to use these. So hydrogen's molar mass from the periodic table is 1.008, oxygen's is 15.999. So step 2, what we're going to do next is we're going to multiply the molar mass for each element by the number of atoms in the compound. So our compound here is water, H2O. How many hydrogens do we have in this formula? Hopefully you shouted 2. How many oxygens do we have in this formula? Hopefully you shouted 1. There's no subscript next to the O, which tells us there's an invisible 1 there. So we have total 3 atoms in the compound. 2 are hydrogen, 1 are oxygen. So to find the molar mass of the compound, I'm going to take 2 times the molar mass of hydrogen, 1.008, and 1 times the molar mass of oxygen, 15.999. So this is step 2 to finding your molar mass. When you do that, these are the values that you end up with. 2.016 grams per mole for 2 hydrogens, and 15.999 for 1 mole of oxygens. All right, step 3. So step 3, the last thing you have to do is add up the molar mass for each atom to find the total molar mass of the compound. So we know we have 2 moles of hydrogen, so 2.016 grams per mole, and 1 mole of oxygen plus 15.999 grams per mole. So when we add these two things together, we get 18.015 grams per mole as the molar mass for 1 mole of water. Excuse me. All right, so what you're gonna do now is you're gonna pause and you're gonna practice on your practice sheet. So you can turn off this video. You're gonna answer questions 16 through 25 on your practice sheet. I have left an answer key in the classroom, so please go ahead and check in with that if you need some help. Hopefully I will be back soon to help you all out, to help you work this out if you have any questions, okay?